Well, welcome everybody joining us tonight for the Astronomical Society of Edinburgh's talk. Before we get on to the actual talk, as usual, if you want to follow us and you're not a member, you can contact and get in touch with us or follow what we do in a variety of ways. The best way is on our website, and there you'll find links to all the other talks that we've put out on YouTube, and you can watch those at your leisure. Okay, next slide, Mark, please. And what we've got coming up is following on from tonight and a whole series of excellent talks, I think, coming up. We have Dr. Bruce Vickery giving another historical perspective on the first Astronomer Royal of Scotland, Thomas Henderson. Followed on Friday the 17th by Professor David Watt from Is Earth Special? And on the 22nd of July, we have the Mission Senior Scientific Officer, Noah Ophie, joining us from Maryland, Johns Hopkins University, to talk about the Parker Solar Probe. And on Friday the 24th, Mark is going to do a Astro Imaging Part 5, and that's about imaging for science projects. And we may find that tonight, it may crop up with Andy Lawrence talking about some potential opportunities. And I think with that, I'll hand over to Andy, but to say that if anybody has any questions and you're on Zoom, the usual, put them on the chat line and Peter will pick them up. If you're on YouTube, if you put them in the comments section, we'll try and pick those up, and then Mark will read those and put them to Andy. So thank you very much. Over to you, Andy, if you want to share your screen.
Thank you. I'll just check. Can you hear me okay first?
Yeah. Fine.
Good. Right. Now I'll make sure the thing is running, and I'll share my screen. Share computer sound. Okay. So we should be sitting on the first slide. It's just got the title, my name, and says ASE July 2020. We okay?
Everything go. Yeah.
Excellent. Okay. Well, it's great to have another chance to talk to the ASE. I love doing it. I'm extremely honoured to be an honorary president and honorary vice president. What is it? I can't remember. What am I called, Andrew?
You're called an honorary president.
Honorary president. There you go.
There's nothing vice
about
anyway.
It's good. So my title tonight is Things That Go Bang in the Night. One of my colleagues has suggested that I maybe should have called it Things That Go Flash in the Night. And later on in the talk, we'll see why he suggested that. Okay, so watch out for that. All right. Oh, no, back one. Sorry, I went to 2 slides there. All right. Now, astronomy, we tend to think of as the sort of grand and stately science. We think of the study of the universe as being about huge amounts of space and huge amounts of time. And actually, the truth is there's a considerable range of timescales involved in the study of astronomy and astronomical phenomena. So let me start off showing you a few of those. Now, it is true that the lifetime of the sun is extremely long. It should be about 10 billion years. So that certainly is a very long time. That's comparable to the age of the universe. But not all stars live that long. So the big hot blue stars last only a few million years. Now, this becomes apparent to you, for instance, if you look at the Pleiades. So we've all seen the Pleiades with our eyes, the Seven Sisters. But here's a nice deep picture of the Pleiades. You can still see the scruff of gas around the Pleiades. That's the remains of the gas that they formed on. Now, the Pleiades formed about 65 million years ago. Now, so here's a curious thought. If you were Stegosaurus 120 million years ago, staring up at the sky and trying to look for the Seven Sisters, well, they wouldn't be there because they were not yet born. So some things last only a few, and soon they'll burn out. So some things only last a few million years. There are plenty of things, as we all know, that occur on a timescale of years in the study of astronomy. So the orbits of planets around the sun. And this nice picture here is, as I'm sure you all know, the retrograde motion of Mars, which was crucial in coming to an understanding of the actual structure of the system that we live in. So that's a timescale of years. There are things that happen on a timescale of weeks. This is the very famous supernova 1987A, which occurred in the LMC. Before and after picture. So the before is on the right-hand side. So it was just an anonymous faint star in the Magellanic Cloud, and suddenly it goes bang, and it fades out over a period of weeks and months. We'll come back to supernovae later. There's some things that happen on a timescale of minutes. Here's a lovely video of a solar flare. Let's see if the video works. Okay, so something dramatic happens on the surface of the sun, and it happens on a timescale of minutes when the magnetic field wraps up on itself and that solar flare explodes out of the sun. Then, of course, a matter of some hours later, the coronal mass ejection associated with that may eventually reach the Earth and play havoc with our electronic systems and so on. And finally, there are things that take place on a timescale of seconds. Now, this is not a real picture. This is an artist's impression of a gamma ray burst. So a gamma ray burst is an enormous explosion that rises, becomes hugely brighter on less than a second, and then fades away over a few seconds. So you see, there's actually a huge range of timescales involved in astronomy. And we really are stuck in the middle of these timescales. Now, to represent a human life, I have there a picture of Vera Rubin, who is one of the great modern heroes of astronomy, discovered the rotation curves of galaxies and how they implied dark matter. Probably, you know, one of the two most famous astronomers not to get a Nobel Prize, you know, Vera and Jocelyn Bell Burnell, of course. But now here's the thing. Taking a human lifetime, you could fit roughly 100 million human lifetimes into the lifetime of the sun. Now, on the other hand, you could fit roughly 100 million gamma ray bursts into a human lifetime. So in that sense, we really are stuck in the middle of time. So that's all about you know, timescales in general. But now moving towards the main topic of tonight, I'm going to talk about unexpected events, because historically and also in modern times, seeing unexpected events has been both very exciting, but also a key part of making scientific progress and understanding what goes on. So we were talking just now before we started about comet NearEarth, the latest exciting comet in the sky. And of course, comets are the classic example of unexpected and exciting events. But you know, for a long time they were a mystery. Of course, one of the key advances was Edmund Halley, who realized that several sightings of comets in the 100 or 200 years before his time were in fact the same comet that was there for on an orbit around the sun. Now I've got a picture there of the sighting of Halley's comet. We think in the Bayeux Tapestry. Halley did not know that that was an occurrence of his comet, but we worked that out since. So that was very nice. But one of the key things here is that it was part of showing that Newtonian physics was correct. Okay, that's how you explained this long elliptical orbit. So it was a victory of the new physics. So here's another example from a few hundred years ago, Tycho's supernova. So it exploded in 1572. The picture on the left is from Tycho's own book. The supernova is star I up at the top of the picture there. And down to the bottom right is what we can see today if we point an X-ray telescope. It's the supernova remnant. The debris from that explosion has been spreading out for hundreds of years. Now, one of the reasons this was important was that in Aristotelian physics, it was assumed that impermanence was in the nature of sublunary phenomena, things in the Earth's atmosphere and below on the Earth. Terrestrial things could change, were impermanent, whereas the heavens were perfect and never changed. So this was the key thing in those historical times that showed that was wrong, that the heavens could change. So an even better example is the Great Comet of 1577, and this illustration is from a woodcut showing the Great Comet seen above Prague. Clearly, even more spectacular than Comet Neowise, I think. This also was important in showing that Aristotelian physics was wrong. Because again, most theories of comets believe that they were atmospheric phenomena of some kind, but this was the first comet that had a parallax. So it was possible to show that it was well outside the moon. And watching its motion, it meant that if Aristotelian physics and the crystal spheres and so on, if that was correct, then this object would be breaking through the crystal spheres. So all those unexpected events, transient phenomena, were extremely important in the history of science. Okay, so this continues to be true until today. So what I'm going to show you now, so modern versions of unexpected events, the importance of transient science. So here's something that's very fashionable at the moment, especially with my colleagues in Belfast, the superluminous supernovae. So supernovae, exploding stars at the end of their lives, have been important for many years, and they're still not fully understood in a variety of ways. But in the last few years, we've discovered that there are rare types of supernovae that are 10 or 100 times more powerful than the supernovae we knew before. And we really don't understand what they are at all. So here's a graph of brightness against time with some typical supernovae of the various types and a superluminous supernova. So they rise up to a peak brightness, which is much bigger than other supernovae. And also they decay more slowly. So the total amount of energy in these things is enormous. So this is a currently fashionable area of research. They're really not, there's some theories, but nobody really understands what they are and why they're so different from the majority of supernovae. We'll come back to those in a little bit. One of the most exciting things, possibly the most exciting thing in the last few years, possibly in the whole of science, I think, let alone astronomy, was at last seeing the first gravitational wave event. So this was in 2015, after decades of developing instrumentation and trying, we finally saw the ripples in space-time that corresponded to two black holes merging. So this is a bit of a technical plot, but this is the frequency of the wobbles of the arms of the interferometers that detect gravitational waves against time. And this curving up, can you see my cursor, by the way? Is that, yeah, okay. So that curving up in frequency. Now, my colleague Roy Williams, although he might be on YouTube, has suggested that I should try and whistle this. So it kind of goes like that, okay? So it increases in frequency and comes to a pitch and then suddenly stops. And that is the process of two black holes merging. So incredibly exciting, proved that Einstein was right, an amazing technological triumph, but also was a surprise, because the measurement of the size of the black holes that merged was much larger than was expected. These were black holes of mass 25, 30 times the mass of the sun, whereas the black holes we knew about in the galaxy from X-ray binaries and so on were 5 or 10 times the mass of the sun. So that is still also a mystery why that is the case. Now, just 2 years later, there was another gravitational wave discovery, which I was very excited to be involved in myself with my PhD student, me and about 3,000 others, by the way. So the a gravitational wave event in 2017 was the first one that had an optical counterpart. Just as and this is the sky map of where the gravitational wave event took off. And at that sky position there is this relatively nearby galaxy. And this is the thing that wasn't there before, that transient event. So it looks a bit like a supernova, but it's what's known as a kilonova. And this results not from two black holes merging, but from two neutron stars merging. And when they do that, you get a flash of light, as well as the disturbances in the space-time continuum that give the gravitational wave event. So the idea that there were kilonovae and that neutron stars could merge and cause this had been a kind of half-believed theory, in accordance with some observations for some time. And this was the thing that really nailed it. And as I'm sure you heard, people argued also that this is how the gold in the universe is made. So that was the neutron star merger. Now, here's my personal favorite, what may be, excuse me, tidal disruption events. Now, here, if this is a picture in 2009 with the Panstarrs telescope of quite a faint galaxy at about redshift 0.15. And here it is a year later. And now it's obviously got a lot brighter, but it's more than you think, because this is just galaxy, and this brightening is just a spot in the middle and the galaxy is underneath it. In the ultraviolet at the same time, here's the 2009 picture, nothing there. 2010 picture, bang. So over the space of a year, in fact, we have a much better light curve than this. Over the space of about a week, it got a factor of 400 brighter, just came out of nowhere and then faded away. So what causes this enormous flare up in the center of a faint distant galaxy? Well, we think it's the tidal disruption of a star. So here's my next movie. The idea is that there's a giant black hole in the center of the galaxy, but which is quiescent. It doesn't have an accretion disk like a quasar. It's not eating any gas. It's not producing energy normally. But every so often, a lone star passes accidentally too close to the black hole. It gets ripped apart by tidal forces. And this is a computer simulation that shows what happens when that star passes too close to the black hole. And basically, some of the material, as it gets ripped apart, some of the material gets thrown back out, and some of it gets sucked into the star and becomes a little accretion disk. And then it's like a little miniature quasar for a few weeks, and then it uses up all the gas and it's gone again. So again, this was something that was postulated over decades, and then finally in about the last 10 years we've seen things we think that's what's going on, this is really it. And now we catch a few of these a year, and it's something that myself and co-workers work on quite a lot. So that's tidal disruption events, very, very exciting. So on the other hand, things that are quasars, it seems, we've discovered in the last few years, can just switch off. This is the spectrum. So this is brightness versus wavelength. So this is red light down here, blue light up here. And this is the spectrum of this quasar in about 2005. And the black line here is the observed spectrum in 2015, I think, 10 years later. It just disappeared. In the red, you can see it is still there. But in the blue, it's just switched off. So these are called changing look quasars. And again, they're my favorites along with tidal disruption events. And then, of course, there's the killer rocks. Again, become an obsession of modern times. So we'll just run this movie and remind ourselves the idea. This is what was caught by a dashboard camera in a town in northern Russia called Chelyabinsk in 2013. Oh, just stop it. Can you hear the sound, by the way? I'll go back and do it again.
Yes, Andy.
So that was a 20-meter piece of rock, a near-Earth object that entered the atmosphere, and there was an explosion before it hit the ground. So that was not from it hitting the ground, but it's the compression impact causes that explosion. And so nobody was killed, but some people did go to hospital. You know, windows were broken and people were hit by flying glass and so on. So that was a piece of rock that was 20 meters across. So you can imagine what might happen if something a kilometer across was to hit a city. Now, some people might suggest if that city was Milton Keynes, we'd all be happy. But no, that's very rude of me. I will pass on. Okay. Now we get to the really new thing and what many of us are concentrating on now. Most of those events, both the historical ones and the recent excitements I've just shown you, they were unexpected events and discovered either as a kind of fluke or by just observing a particular patch of sky to look for something. But really, as I'll show you in this next section, to really make progress in some of the scientific problems that these bring up, what we really want to do is systematically sweep the whole sky again and again to find large numbers of objects and to find rare objects. Now, in the next few slides, I'll give you a feeling for why that is so important. So firstly, back to the near-Earth objects. Here is a lovely little GIF. This is the orbits of all the known near-Earth objects as of January 2018. I think this video is from WISE, but I can't quite remember. But it's from Wikipedia, of course, actually. But anyway, I think it's from WISE. So here's the thing: the key point I'm making here is that there's a lot of them, right? But we know there are many more that we simply have not discovered them all, especially the modest sized ones. And above a certain size, many kilometers, we probably know them all. At 20 meters or less, we probably don't worry too much. But in the range of 100 meters, a kilometer, 5 kilometers, they can be absolutely deadly, but we don't know they're out there. So people are desperate to find them all. Okay, and as you probably know, there's a NASA mandate to go find all the near-Earth objects down to, I think it's down to 200 meters is the desire. So we need to find all the near-Earth objects. Here is a graph, so a bit technical again, my apologies, but this is a graph that demonstrates the discovery of dark energy of the accelerating universe. This is to do with supernovae, supernova, a particular type 1 supernovae, type 1a supernovae. And for these two projects, the High-Z Supernova project and the Supernova Cosmology project, so what they've got here is for each of the supernovae, there's the estimated distance based on its brightness and its redshift, so it's kind of cosmological distance. And the black line going through the middle is the prediction of what you ought to see if in the standard cosmology without dark energy. And then in this plot below, you subtract all those values from that predicted line and you get the so-called residuals. So you can see if it's ordinary cosmology, the points ought to go through that line on average, but they're systematically above the line, and as they are also in this project. So this was the evidence that the universe was accelerating and that there is dark energy. But you can see, it's really not as good as you'd like. So to really nail this problem of understanding dark energy and to measure it, exactly which variation of this curve are we looking at? Does the acceleration of the universe change with cosmic epoch? All those sort of questions. You need not a few tens of supernovae, such as was studied here. You need thousands of them. Okay, but to get thousands of supernovae, this is the problem. You just know they're somewhere out there. Okay, so you can imagine there's supernovae going off in some distant galaxy all the time, but they could be anywhere. So you can imagine this picture going twinkle, 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 things going off here and there. If you're not looking in the right place, you're going to miss it. So what you need to do is to survey lots of sky to catch the supernovae and get large numbers of them. There's a similar story with my favorite objects, the tidal disruption events. So here's a picture of a nice big nearby galaxy. Does anybody recognize that actually? Do we know what it is? I should know. No, all right, don't worry. See if anybody can spot it by the end of the talk. I can't remember. So suppose there is in the center of that galaxy a black hole which is quiescent. The prediction from theory is that in a quiescent to dark black hole, that tidal disruption thing where a star goes too close, it's going to happen about once every 100,000 years. So if you want to study this phenomenon in this specific galaxy, you've got to sit and watch it for rather a long time. So that simply is not going to work. So the answer to that is you've got to keep monitoring millions of galaxies. And then you can expect that at least a few of those each year will go off bang. So that's what you need to do. So you see the consistent picture here. So this is why I refer to this as factory mode transient studies, the factory mode study of unexpected events. We need to keep sweeping the whole sky, or as much of the sky as we can, big wide areas, do it again and again and again, on a timescale of every few days, something like that. So to do that, we need deep wide angle imaging telescopes. So that's what we have in the next part of the talk here. So this idea of doing kind of factory mode wide angle surveys, it started with relatively small facilities. So I'm sure you've heard of some of these. This is Super WASP on La Palma, and it's really like a sort of a collection of fashion photographers' wide angle lenses. Each one of those pointing in a slightly different direction, so you can capture a whole bunch of sky in one go. This is one of the telescopes from the Catalina Sky Survey, and this is the telescope used by the TRAPPIST survey. So this is a 60 centimeter telescope, so it's getting a little bit bigger, but it's still not that big. Now, most of these projects have been used looking for exoplanets, which is of course very exciting and a very modern, fashionable thing. Also some variable star studies, but these things are not good enough for this sort of things that I've mostly been talking about in this talk, the quasars, the supernovae, the near-Earth objects, and so on. For that, you need telescopes which are a bit bigger. So the first serious attempt to do that was this beast, Panstarrs. So here it is on Haleakala on Maui in Hawaii, and it's a 1.5 meter telescope. And here you can see this is the point. This is the camera. So this is a CCD camera. This whole thing. Each one is a mosaic. Each one of these little squares is a CCD, and so they're kind of butted together to make this giant camera. Now, by the way, this is quite a technical challenge. Getting a wide angle view and a big CCD camera like that is, for reasons I won't bore you with, it's much harder to do with big telescopes and small ones. But they did this very nicely, and got about a 7-degree field of view, so about sort of 14 moons across. And so they kept kind of moving around the sky. So where we are now, a project that a lot of us are involved with is the Zwicky Transient Facility, or ZTF. It is an American project, so I will call it ZTF and not ZTF, okay, in honor of the Americans. So this is actually a repurposing of the very famous Palomar-Schmidt telescope. So some of you may know that the Palomar-Schmidt, like the UK Schmidt, used to take glass photos that are about this big across and were 6 degrees on a side. And you can see this technician here holding one of the filters from the camera on this telescope. And it's about the same size as some of the Schmidt plates some of you will have seen. So that's surveying the sky now, and I'll show you some more results from that in a moment. And then, of course, the big thing we're looking forward to in the near future is what used to be called LSST, the Large Synoptic Survey Telescope. It's now been renamed the Rubin Observatory in honor of Vera Rubin, but they still retain the LSST. So it's decided this is the name of the observatory, but the survey that it's going to do is the Legacy Survey of Space and Time. So this is now a 10-meter telescope, but with a wide angle field of view. So it's just going to be amazing. And this is it looks beautiful, it looks like a painting, but this is a real photograph of LSST. It's almost built now and should start operating in 2023. It was, of course, due to, it's been delayed by 6 months by the pandemic, like everybody else. But it's well under construction. So that's going to be very exciting. Okay, so those are the facilities, big telescopes with wide fields of view to get massive samples of objects, but also to get rare objects, one or the other of those things. If you could just hang on for a second. Sorry about that. I was just shutting the lounge door. There's a risk that means the dog will bark in a minute because she can't get in, but we'll see. Okay, so that's our big new facilities. Now I'm going to get to telling you about the Lhasa event broker. Now Lhasa is it's a word which works in both Gaelic and Irish Gaelic. And it means flash or flame. So it's a very appropriate project, we think. And it's a collaboration between Edinburgh and Belfast. So that kind of Scottish-Irish connection made us feel it was a very appropriate word, together with the flash or flame idea for transient events. Right, so what's an event broker? What's that all about? Well, here is the ZTF facility again, the telescope with the camera. Now, this is the way it spots transients. It does its first image of the whole sky. And by the way, it kind of reobserves the whole sky, the whole northern sky, at least every few days. So it's pretty impressive. And so it gets a kind of map of the whole sky. And then when it does it again, as it goes to each little section of sky, it takes the new image and the reference image and it subtracts one from the other to look for what's changed. So here's an example in a very small piece of sky. This is the reference image and this is the new one. And you can see there's something there that wasn't there before. Now that's pretty obvious by eye in this case, but when you do the difference images, it's known, most of it's noise. And then there's this thing in the middle. So you subtract all the time and you look for objects in the difference image, and that's how you find events which are changing. Now, the amazing thing about the sky is that when you get down to these sort of depths, there's stuff going on all the time. So ZTF sees thousands of alerts per night. Now, astronomers don't get them directly from that telescope. What happens is that ZTF packages them up into lots of little event packets with information and sends them out as a stream to 2 or 3 different brokers. So it's broker just like in, you get your insurance through a broker instead of directly from the insurance company. And the same thing is astronomers get the events from us rather than directly from ZTF. So they pump out the stream of events, thousands a night. It arrives, here's ROE, beautiful, isn't it? Arrives in Edinburgh, gets put into our computers in the Lhasa system in a big database. And then astronomers all over the world query our database to, in a way I'll show you in a moment, to get things they find interesting. And then they do stuff with it and they make science. So here's a supernova light curve made from ZTF data. So how does this work? What do they actually do? Well, here's the website. You can go and see the website for yourself. lhasa.re.ac.uk. So at the simplest level, this is this screenshot here is the sky coverage. So every night you can, every few days or over a period of month or whatever, you can look at how much of the sky has been covered, how many events are in different parts of the sky. This here also, whenever there's a gravitational wave event, we plot that over an overall sky image so that people can see where on the sky the events happened. And also those yellow dots there are marking the positions of the 200 galaxies that could be candidates in that particular piece of sky. Right, but now this is often what people do. Suppose you've got an object you already know about, some supernova that you're studying, but you're thinking, oh, is it in the Lhasa database? Has it been seen by Lhasa, by ZTF? So you go up here into the search box, you put the coordinates of the thing that you know about. Here's an example. Again, this is a pretty faint, fuzzy example, but here is the object. And if you do that, you get back the light has been seen, that object has been seen by Lhasa many days in a row. And here is the light curve, and this is pretty obviously a supernova in this case. Now, on the other hand, what you can do this, you don't have to know. So that's, if you already know what you're looking for and you go and look for it in the database. But in this case, what you're doing is running queries, like for instance, this one here, this is known as a filter. You say, I want to just go through the database and find me everything that looks like a supernova that's happened in the last 14 days. And so these are some pre-packaged ones that we give people. So you can say, run that now and see what I get. Now, just to frighten you, this actually corresponds to this bit of computer code. This is what's known as an SQL query. It's how you query a database. It's the same language you use for query, that the people at Tesco used to query their database of, customer transactions or whatever. It's the same stuff. But you say, find me everything that was brighter than this, that goes down faster than this, that's got a color like this, that was, in the last 14 days, blah, blah, blah. So you give it lots of sort of constraints when you query, and then you say go, and it goes off the database and finds them. So if you run that particular query there, so I ran that last night or 2 nights ago, and this is what you get back. So then you get a list of objects and some of their summary characteristics that fit what you're looking for in your query. Here's one here. And then when you get out the light curve, this is a lot more boring than the previous light curve. And see all these grayed out points, they're all upper limits where nothing was seen. And then suddenly, bang, there it is, 2 magnitudes brighter. So as I say, that's a relatively boring light curve, but here's the point, that you're onto it early, right? And that means now you know something's happening. If you think, oh, this one looks interesting, then you tell your chums and you say, can we point the X-ray telescope at this one? Can we get some different wavelengths? Can anybody else observe this? Right. So that's the sort of thing that people do. So as I said, this is a sort of pre-packaged query that we suggest to people. But the idea is that other astronomers write their own to get just the events that they want to find out what's happening in the sky out of those thousands per night. And by the way, of those thousands per night, half of them are junk. A lot of them are just flare stars, M stars that are flaring or something, or other variable stars. So only some of them are going to be interesting, but you have to weed through a lot of stuff to get to the interesting and exciting things. On the other hand, we have the idea of a watch list where, so here it's not completely unknown. You know about the objects, but you provide a list of objects to our database. So for instance, a sample of cataclysmic variables or of BL-LAC objects or of AM Canven stars. And you say, can you please, no, here's my list. Can you compare this list of things against the database every night and tell me if one of them does something? Okay, that's the idea. We're working on a system where at the moment you run that and you go and check the database, but pretty soon that's going to be a proper alert system where you get a text message or something. Okay, that's the idea. To show you an example then, this is again, I just picked one pretty much at random, that watch list of cataclysmic variables. This is what's been going on with this particular object. So you see cataclysmic variables, of course, are very erratic variables. And this is AM-HER, the definition object of the AM-HER class of variables. And that goes both up and down and waggles all over the place. So some people love these variable stars, not my own field, but the other reason I was showing you these is that most of the things I've been showing you so far are pretty faint, but not everything in a database like this is. So you can see here, AM-HER, a lot of the time is 14th magnitude, and every so often it's 11th. So it gets quite bright sometimes. Okay, so this is my last section. What I'm going to say to you, it's not nearly as well developed as the stuff I know that you've heard about Exoclock and the HOIS project and so on. So this is me kind of thinking aloud, but interesting to see what you think about this, because it just occurred to me to wonder whether excuse me, whether this is an area and transient science, deep transient science even, where we ought to try and encourage amateur astronomers to get involved with the science. So as you know, historically in this area, it certainly is an area where amateur astronomers have been very important. So here, for instance, is the very famous nova hunter, George Alcock. So in 1967, he discovered Nova Delphini, and then he discovered loads more after. He discovered lots of comets as well. And here's a very lovely light curve from the astronomer in 1968. I believe, and I believe this because Wikipedia told me this, and Wikipedia never lies, of course. I believe that in order to do this, when he found Nova Delphini, he was sort of combing the sky, sweeping the sky for a total of something like 800 hours, and then he spotted it. So he was doing a kind of human version of what we're trying to do now robotically, this conclusion that to get rare things, you've got to cover a lot of sky again and again. Now, on the other hand, of course, historically, amateur astronomers have been very important in studying variable stars, because there are so many of them, and this is true particularly in America, but also in Britain. And of course, the idea is there are a large number of variable stars, and professional astronomers, even those for whom it was their research subject, couldn't spend enough time to watch all of them. So astronomers watching them, amateur astronomers watching them, would have a very important role to play in collecting data. And here over many years is the beautiful light curve of SS Cygni, with its wonderful recurring outbursts. Very interesting because it's not quite periodic. It looks like it almost is, but it isn't. That kind of object is extremely interesting. Now, some of this need has gone away for exactly the sort of reasons I'm describing to you, that astronomers now have got obsessed with factory mode surveying. So now the whole point is that things like Panstarrs, ZTF, LSST are sweeping the whole sky. But also in monitoring objects, you know, you saw the light curve of AM-HER, so you know ZTF is seeing it every few days. So you might think that kind of takes the rug from out under the feet of amateur astronomers, but I think we have to think about, you know, what ground is still left, what's important for amateurs to do. So the first thing I think is higher time resolution. So this is where I think that, for instance, the Exoclock project is very nice. I watched on YouTube that talk the other night, and I saw Mark's light curve. So the eclipse that was all observed during one night, Mark. Yeah. So you know, whereas ZTF, wonderful though it is going back to the same bit of sky every few days. So you can't do that sort of fast work. So that's still something that can be done by amateur astronomers, but I think it's not what I'm talking about here. But what else could there be? Well, the new fashion, of course, is citizen science. Now, this is where not just amateur astronomers, but the general public have got involved in all sorts of projects. It all started with Galaxy Zoo, as I'm sure you know, but Zooniverse now is a whole universe of projects. I was thinking actually there ought to be a project where people sort of identify animals in zoological gardens, because that could be called Zoo. I just think that ought to happen. But anyway, onwards. So there are now quite a lot of Zooniverse projects, but here are two that are already up that are related to what I've been talking about. There's a SuperWASP project. I'll show you an example of what goes on there in a moment. And there's already a Zwicky related project, which is relatively simple. It's basically about weeding out. It throws up light curves and says, do you think this is real or junk? Right. So that is quite useful. But in the Lhasa project, we've been developing with some of our colleagues in America and Oxford, we've been developing a project on superluminous supernovae. Now, this is not yet an official Zooniverse project, it's in draft stage. But pretty soon we're going to need some beta testers to help us improve that. So that's certainly something that's on offer. Let me show you the sort of thing that happens. I don't know how many of you have tried Zooniverse projects in general, but this is fairly typical. So this is the SuperWASP project. So when you say, give me the next one, it throws up a light curve. So it's very noisy, but also has a kind of averaged light curve. And you have to look at it and decide, all right, is that a pulsator or an eclipsing binary or a rotator or what is it? And you do some training of different types and you click through these and choose them. And that's what you do as a citizen scientist. So the similar idea we're working on for the Lhasa project to do with ZTF things is about superluminous supernovae. So already in the data, we got things that show light curves a bit like that kind of look like supernovae. But the question is, are they superluminous supernovae? And it takes quite a lot of work to decide, but you know, the human eye going through them can help here. And at the moment, there are two things to look for. One is when you look at this rise time, with a normal supernova, that's quite fast. And with a superluminous supernova, it can take over 20 days. So it's look at this and tell me whether the rise time is more than 20 days. And the second thing is to look at the image. Basically, you can see this thing here occurred in the outskirts of a pretty big normal nearby galaxy. That will not be a superluminous supernova because it's not. You need something very faint to know it's far enough away that it must have been superluminous for you to see it at all, as it were. So if you see something in a faint fuzzy galaxy, that is also a sign that it's a superluminous supernova. So that's what some of my colleagues, especially Roy Williams and Meg Schwamm and a few others, and the guys in Belfast, have been working on with people from Oxford and Minnesota, and hopefully will get released sometime in the autumn. So that's citizen science. So that's obviously something that amateur astronomers can do, but I find myself wondering if there's other things that you can. This is my last slide, by the way. So one thing is to take more observations when when an alert is triggered and it looks particularly interesting, to get people around at a range of latitudes and soak it, and really get a thorough light curve that's well sampled. Do it in different filters, and so on. So that is one possibility. Now, for many of the things I've been showing you, that's pretty challenging for most amateurs because the sort of objects we're talking about are often quite faint, but not all of them are. So it may push that back towards outbursts in variable stars rather than the supernovae or tidal disruption events. But if somebody thinks they can catch something at 18th magnitude, then it's doable. But I guess, well, we can talk about this in a second, but I think, for most people's equipment, they're probably mostly a bit too faint, but maybe there's something there. The other possibility that occurs to me is that maybe technically minded and more ambitious amateur astronomers can get involved in doing the discoveries through the database, because there's just tons of stuff in there and we don't know what the hell it all is, essentially. Now, so if you can learn how to run queries, to set up your own kind of research projects and do it through the database, maybe there's something there. Now, the obvious snag with this, however, is that, I showed you this piece of code. A lot of it, the way it is at the moment is rather techie. So no, some people will do this sort of stuff, but I think not many will. But if there's enough interest and it seems useful enough, then maybe we should be thinking about designing an interface that takes those technical details away and does something that builds it in a more simple app-like kind of manner, so that people can find and share discoveries and feed them out to astronomers' telegrams, to the Transient name server, and so on. So I don't know, as I said, this is me sort of thinking out loud, essentially, because apart from that draft Zooniverse project, unlike your Exoclock chums, we don't have something ready-made for you to say, this is what you do. So it's me thinking aloud and wondering what opportunities there may be. But that, ladies and gentlemen, and others, is all I have to say for you today. Yeah, thank you very much.
Brilliant, Andy. Can I ask people to unmute and show our appreciation? Terrific, Andy. I thought that was a difficult topic, technically covered with aplomb. I was only disappointed with one thing, that when you showed us a picture of the sky and suggested there were supernovae going off, and having heard it was things that go bang in the night, you managed to twinkle, twinkle, twinkle. But apart from that, fine. As a seasoned Zoo Universe user, I think it has lots of legs. There's a whole host of talent in the amateur world, isn't there? People who enjoy the techie stuff, enjoy the computer stuff. So I'm sure there are routes to tap into it. Anyway, let's get on to the questions. I'll hand over to Peter first. Okay, well, we'll avoid the conversation about Milton Keynes. And Nigel, you were asking about Starlink.
Yes, I was. Thanks very much, Andy. That was fascinating. I just wondered, with your research resting so much on continuous wide surveys of the sky, how much of an impact our friend Elon Musk is going to have on that.
Yeah, quite a fair amount. So it's hard yet to tell exactly how much, but obviously some. I think it's not bad enough that it's going to completely ruin this whole idea. But basically, it's going to make everything harder work. And in one of two ways. Firstly, that simple idea that you subtract one image from the other and you go, oh, look, something happened there. The software is going to have to be a lot cleverer, because when you have all these streaks, and especially if the satellite's rotating and does periodic flashes as it rotates, for instance, that's quite often going to get mistaken for a transient. So there's going to be way more junk than before. That's one thing. So the software will have to be cleverer, work harder. The other way it'll have an impact that I know the Rubin Observatory people are trying to talk to SpaceX about is to get orbital information about the satellites, to try and plan the sequence of observations to avoid them. Now, of course, as you know, they're mostly at in twilight or just after, early in the night and early in the morning, as it were. But that's quite a lot of time that's extremely useful. So it's not going to kill things, but it's going to make things very hard work. Now, wearing another hat to mine, another thing that everybody talks about and has been discussed is the idea of painting them black, so that they're just not as shiny. If they do that, that will make things better for optical astronomy, but it'll make it worse for infrared astronomy. Oh. Right. Because that energy's got to come out somewhere. Yeah. And I know, and I'm also part of an infrared survey. So yeah, it's very difficult to completely win. So yeah, we're all a bit nervous about that. It's not a complete disaster, but it's pretty bad.
Right. They said last week at the EAS meeting that the black paint's off the agenda because the satellite gets too hot. They're now doing sort of umbrellas and things, which may be better. But I think the other problem that the LSST people, Vera Rubin's Observatory, was saying is that they're so bright that the CCD saturates and you end up with a trail you can't remove. So basically they're saying they don't know where they're going at the moment.
No, that's right. It's not just, you're quite right, John. It's not just a question of a simple streak.
No.
It'll obliterate quite a large number of pixels along that streak, because
and of course it's likely to overflow the pixels because it hasn't got anti-blooming on.
Yeah. So yeah.
They weren't happy at all last week in the meeting that went on.
No.
Well, thanks very much, Andy.
Thanks for that. Mark, you had a question next.
Yeah, a few of us have been working with the HOIS project recently, and they've just got some LCO telescope time, which we've been using. It strikes me that the Lasair and stuff could feed in quite nicely to that, because could, for example, it work out an object has changed its brightness from magnitude 16 to 15? And also, does it image in multiple filters or just one?
Yeah, so this is one of the ways in which LSST will get better, because ZTF is in 2 filters, G band and R band, so roughly green and red, and LSST will be in 6, U, G, R, I, Z, Y. So LSST will have a lot more. But at the moment with ZTF, that's one of the reasons, for instance, for follow-up observations. If you want to know the multicolor evolution of something, then you need to get on it with some other telescope that's got some filters. So that's a possibility. But I think, is it Dirk Frobrich?
It is, Kent?
Yeah. So I'm trying to remember whether he's part of our consortium. So we have the kind of UK branch of LSST, and it's so that's a project we actually have money for, and it's off the back of that we've done the ZTF work. So it may be that we should be talking to Dirk to get him to, for instance, to put one of those watch lists in, or some sort of filter that becomes the feeder for something like that.
Yeah, I mean, if for example you set up, they have about 30 target regions. So if, for example, you set up a standard event that if any object in that increased in brightness by 1 magnitude, could that be a standard sort of notification that was sent out? And then the idea would be that he would then send out to all the people on the HOIS project to monitor that area in all the filters for as often as possible over the next few months. That's the sort of thing that seems to happen with Gaia alerts anyway.
Yeah. Now that's exactly the sort of thing that the system is designed to do. So as the Lhasa project, we don't provide those things ourselves. It's a kind of framework where people can build their own filters, queries to produce that sort of alert.
Yeah, no, it sounds really useful for that project, I think, might do away with diameters, actually.
Peter, can I suggest we relieve some frustration here? The pronunciation of this name, I think Sean has a view on it. Sean, are you there?
Yes, I am, but I wasn't intending to speak on that issue. It's pronounced perfectly fine.
I assumed that's what I assumed you were giving congratulations there.
I was being congratulatory, absolutely.
Yes. So I can tell you will not be surprised to hear, Sean, that it's very hard to train our colleagues to say it. So most people end up saying Lasair. What confuses people with the Gaelic is the stress is on a different part of the word. It's Lasair rather than Lasair, but you're getting it right. You're pronouncing it right. Okay. At first, I thought it was something to do with the capital of Tibet, but it's not. Great. So now, I have to say, so as I say, it's the Irish people involved in this project are all from Queens and Belfast. They're not from the Republic.
No, I understand some of the difficulties involved, but thanks for a wonderful talk. It's excellent.
Okay, can we move on to Neil? I think, Neil, you had a question about the data dictionary, which sort of ties in with the Ian Smith's question about whether it's small enough to be downloaded. Maybe we could deal with both at the same time.
Yeah, first of all, I'm glad you tackled the pronunciation issue before my question so that I didn't have to say the word again. Yeah, Andy, thanks. That was fantastic. Really enjoyed it. And the idea that we can contribute as amateurs is really appealing. So I wondered if the data dictionary for the database is published so that it can help people to write queries, and that might lead us to being able to write a natural language interface that would extend the reach of the database to other amateurs who are not as technically comfortable with SQL, for example.
Yeah. So to take the first part first, yes, and the second part, not yet. So I mean, there's quite a lot of guidance on our web pages about how you construct a query, what all the column names are, what they all mean, some examples of how you do different things. There's a kind of cookbook now, and of course, all that is aimed at professional astronomers and people who know a bit of SQL and so on. It obviously is possible. When your idea of natural language processing is particularly ambitious, I was thinking of maybe something a bit more packaged up with drop-down boxes and so on, should already make it a lot easier. Natural language processing sounds fantastic, but it's quite ambitious. Both those things, they're non-zero amounts of work. At the moment, I don't see us doing that ourselves much, though we'd love to. Sort of thing that we might hope some PhD student might have a go at, but also some keen amateur sort of skilled computer science types, also could have a go. So. At the moment, one of the things we are doing is working on the API, the application programming interface, which should make that sort of thing a bit easier. But yeah, it's all very well defined and described and documented. So that starting point there is good.
Okay, great, thank you.
Very good. Ian,
Take a look.
did you want to amplify your question a bit?
Yeah, I can sort of imagine citizens and sleuths mining the database, looking for events, and but it worries me that if we all pile in, it might load your servers a bit too much. So I was wondering if the database itself is sufficiently small for us to download and query it on our own PCs.
I should think that'd be sensible. So I don't know what the size is at the moment, but it's it's terabytes. So it's not really sensible.
Yeah,
and growing on, and it'll be much bigger for LSST. But also that's kind of not the right approach to life, because we have to ask that question for for regular astronomers around the world, as well as the potential of amateur and citizen involvement, as it were. So really one of the things we're doing at the moment, and that the LSST project pays us to do, is to test performance and reliability and just get everything faster and so on. So that's the right approach. And actually what we usually worry about is not lots of people, but it's the occasional the occasional clever but stupid user. So people who write queries that do the same thing billions of times in the script. When you think, no, don't do that. So that's when we're trying to talk about how to put in throttles on the system to try and control overambitious grad students and so forth. But I think that sort of thing is more likely to be a problem than lots of people running smaller queries, I think. But it is something that always has to be borne in mind.
Very good. David had a comment. I don't know, David, did you want to follow that up?
What I was suggesting is maybe just get a sample of the database, not the whole thing. That'll at least let you put on as an SQL server yourself and play with it.
What that could well be possible. Yeah, I mean, I don't necessarily see the advantage of actually having a copy as opposed to trying some trial queries on the real thing, if you see what I mean. But maybe that's better. That's something.
It just allows you. It just allows you to play with it without breaking the real thing.
Well, hopefully it's set up in a way that is not easily broken. But some of these questions, a lot of very interesting technical questions, which next week I'm going to have to ask some of my technical chums. I'm just the scientist.
Well, being an operational technical person, I would be dead scared of allowing lots of people to suck bits of stuff out and analyze it in a way that might not be consistent with the data. And then, they start saying, I've discovered such and such from this data, when I've not really.
Oh yeah. That's. I mean, well, believe me, again, that's potentially a problem with normal scientists, let alone random amateurs. So, but yes, that's that, Peter, is a more significant problem. I think that people will manage to do things, but they'll do things that aren't scientifically rigorous, as it were. Yeah. So I think some of the time the answer to that, as we've seen a lot of times in other amateur involvements, is amateur professional partnerships, basically, where people work in collaboration. I think that's the way to avoid that. But to some extent, so the US guys, by the way, are very keen on opening up the LSST data to schools projects. There's a little bit of that going on here, but not so much. But they're very keen on that, and people have made exactly the same kind of worry that, well, are they just going to produce nonsense? But the thing is, if you do, so what? It's fine. It really is nonsense, and you tried to publish it in the Astrophysical Journal, it would only get refereed and rejected anyway. So, you go through the same tests as anybody else. So it's maybe not, and if you if you send it to the Daily Mail, nobody will believe it anyway. So, you know, it's all the same, really.
No, it may be the opposite. Send it to the Daily Mail and believe it. So,
well, yes.
Could I ask a question before we finish? I'm just going to make a point on two of the things that were said along the way. One was, I think, by you, Andy, where you said that the student may well put in a query that just runs forever. One way of getting around that would be to have a pre-processor that looks at what it's about to do. And there was another question about having a small part of the database, I think from David. Perhaps you could actually take a copy of part of the database and students could log into that first and learn how to do all these questions so they don't do the billions of questions.
Oh, yeah. Those are both quite good points. So by the way, at the moment, the main thing, yes, the pre-processing thing is exactly what we've been discussing recently, actually. But what we already have is, for instance, is an extraction row limit. So at the moment, you can't suck down an arbitrarily large subset of the database. The software stops you doing that. But if we had, once we have more intelligent pre-processing and testing, then it may be that we can allow that if we can see it is for a sensible reason, for instance. But that, at the moment, the throttling is there, but quite crude. But yeah, very interesting points. I thought you were going to tell me something in my history bits was wrong, Bruce.
Oh, get away with you. I'm not into the same history as you. Who's Xerxes, the son of Darius?
So, he's the guy who invaded Greece in the 3rd century BC.
I was wondering, Andy, if the whole idea of King of Kings had gone to your head that was his title, wasn't it? Of Persia, he was the King of Kings.
It's actually because I've always been known by a large number of my colleagues as Xerxes, because I started off life as an X-ray astronomer, and I only had 2 initials, but I needed 3 for my username on the computer system. So I became AXL, and people decided this was because my secret name was Xerxes, and it kind of stuck. So I've been Xerxes for many years.
I think we better see if there's any questions from the YouTube group. Mark?
That's been quite quiet on YouTube. Lots of people on it, but it's been quiet as far as comments have been concerned. So no, nothing from there.
Okay.
Lots of people there though.
Well,
can I ask a question?
Oh, absolutely.
I think my big problem with this and other things like this is how you ever get it published. That seems almost a bigger hurdle than actually finding the objects and things in the first place. Because I've got a couple of things I've found in the Gaia data, but trying to actually write a paper, even a research note for something like the American Astronomical Society research notes is quite a challenge, really. I just wondered if there's any advice on where we could go on such things.
Well, it depends what you mean by publish. This is the first thing. So, so some people, and there was always been astronomers who've done this as well, who, when they see something unusual, noteworthy, publish a note on astronomers' telegrams or similar. You know, that's the name of that's evolved over the years. I'm not sure what it's called at the moment, but so just saying, hey, I found this interesting thing. Here it is. Go look at it. It looked like this. And it's a short note. It gets circulated around. A lot of people pay attention. So if that counts as if that's publication, then that's relatively simple. You got to learn to write that in a really succinct kind of way to get that across. To actually, write a real paper, the thing is, because of factory mode, this has got harder than it used to be. So at first, finding weird things, you could kind of go, look, and that was enough to get something published. You could say, look, that was weird. Look at that, right? But now, if you do it, you go, look, and people say, yeah, saw 5 of those last week. So you've got to go on from there to the point to do the science. You've got to observe it multiple times, get the shape of the light curve, think about what that means. So it's only the start of the process is the discovery. So that's another reason I think for potentially for amateurs to have fun with this. it makes more sense to do that in some kind of collaboration with professionals who can do the other part of the work, including, you know, writing papers is a difficult and challenging thing to do in itself. You know, I mean, our PhD students, there's a lot of what they take 3 years to learn is how to write. It's very, writing technical material is very, very difficult. Much harder than people realize it's going to be.
You have to get over the fun and games of latex, of course, first of all.
Absolutely.
Which some of us are not exactly familiar with. So that's about the second or third challenge as far as I'm concerned. The other thing I was going to say is, of course, that the ZTF database itself you can actually query. I actually got the data for the one that Mark's been looking at, V1490 SIG last week. I was actually looking for, I think I was looking for something completely different, but that's a fairly simple interface. You just put in the position and a cone search length, pick the object you think it is, and then you can just download the curve quite easily.
Yeah, so for the, I think it's 3 years now it's been running. So the final finished survey database,
yes,
they publish themselves and you access it through a database at Caltech. So what we know, so what we're talking about here is the you know, events which occur night by night, whereas their data release they do every 6 months, a year, or something like that. But yes, the final finished database is all there. And one thing we want to try and put that inside our event database as well, to make it easier to join the two up. But at the moment, you have to do it two different ways. You find the thing, and then you go and find other things, or the whole light curve in the original ZTF database.
And of course, you've got the Gaia transients as well, popping out a few tens a week. So I don't know whether do you look at those or compare your data with those?
Yeah, so in fact, my PhD student at the moment is working on a Gaia transient that we've been following up in Lhasa with the ZTF data, because that was, and so I have some colleagues that I work with on Gaia alerts, and there was an object which one of my colleagues picked up, which seemed to have got 1 magnitude brighter in the Gaia data over a period of a year or so. So not very fast, but just steadily rising.
Yes, a few of
so
those.
I went to find it in Lhasa, and this is where the difference imaging comes in. That was actually in the center of quite a big galaxy, and Gaia's got quite a big aperture.
Yes.
So it included lots of starlight in what it was measuring. Whereas with ZTF, we subtract the galaxy and it leaves only the thing in the middle that was changing. Yes. And we found that it hadn't changed by 1 magnitude, it changed by 3 magnitudes.
Oh, right.
So it suddenly became much more interesting by putting those two data sets together.
Yeah. Was the other one was that micro lensing thing that the Polish astronomer was investigating? It was a binary star that went in front of another star.
Yeah, well,
there's a load of ZTF data in his analysis as well as others.
Yes. So for some of those microlensing events are very interesting, and so I didn't mention those, but they are potentially of amateur interest again, or follow-up interest, because I said maybe, you know, the ZTF data is. If you're lucky, you see something every 4 days, and if that particular night was cloudy on Palomar, it might be every 8 days. Okay, so for a supernova, that's usually okay. It's good enough to get the light curve. But for a microlensing event, you can miss the peak, which can go over a day or 2 or 3.
Yes.
So you see something rising, and that's when you say, "Jump on this, guys!" And you know, and other people do the fine time sampling, and that's when you want people at different longitudes as well, to make sure you don't, you know, miss a few hours.
The other thing with microlensing, of course, it's a one-off event. It happens, and if you miss it, goodbye.
Yeah,
never to be seen again.
Can we see if there's anyone else got a question?
No, we all done. Well, Andy, as somebody who, admittedly, a few decades ago, wrote a query on the company mainframe, and they wondered why they never processed any orders that night. I wouldn't like to get involved in that sort of thing, but I think things have moved on. Again, thank you very much. Fascinating, very interesting. If you're looking for some test buddies, I'm certainly interested in any Zoo Universe type involvement. So brilliant. Again, can we just thank Andy again? Brilliant. And if anybody does have any further questions, I'm sure you can email Andy and he'll respond. Thanks again, and good night.
A pleasure as ever. Nice to see you all.
Cheers.
Thanks, good night.
Night all.
Very good. Okay.
Bye.